but by flow. And the ice flows toward the coasts and then becomes icebergs. So as we go deeper, these yearly layers become thinner and thinner, and after 2 miles, or after 2.5 kilometers, they become as thin as your fingernail. Then we can no longer count. In Greenland, the deepest ice is about 200,000 years old. In Antarctica, we didn't reach it yet, but we think that in some places the oldest ice is 1 million years old. The reason that we keep this ice, the reason that we spend all of this money on airplanes and electricity to power the freezer is because if we make certain measurements on the ice, if we do certain science experiments, we can get some information from the ice about Earth's climate in past times and about history of the Earth's atmosphere, including amounts of greenhouse gases such as carbon dioxide and methane. So from the ice, we can get this information for maybe about the past 1 million years of the Earth's history. Well, let me tell you a little bit about the science, and then we can go inside for a short time and look at the collection. We want to go inside for only a short time because in here it's negative 24 degrees, and in the larger back room it's negative 36 degrees. So Celsius. So with summer clothing, short time is best. Well, you know, if you have a snowball, it's not as heavy as ice ball, and the reason is that there are spaces between the snowflakes which are filled with a sample of the Earth's atmosphere, air samples in a snowball. Now, maybe if you take a snowball and put it to your mouth, you can take a breath. It's an open network. If there's some wind, the air in the snowball can be pushed out and replaced by the air in the wind. But when a layer of snow is buried deeper and deeper, the snow is compressed so that the open network of spaces in the snow is closed off into individual bubbles. When that happens, the air is trapped, and no matter how old the ice is, we can look at those bubbles and determine the composition of the Earth's atmosphere at the time represented by the age of the ice. What we do is we take a piece of ice from a time of interest and we put it inside a jar, and with a vacuum pump we take today's air out of that jar. Then the ice melts and the bubbles under pressure pop and return their air to the interior of the jar, and we can measure it, and we can determine the amounts of carbon dioxide, methane, other gases in the Earth's atmosphere at this time, and then we can compare it with this time, or we can compare it with what we have here now to see changing amounts of greenhouse gases over maybe about 1 million years of Earth's history. Another scientific piece of information that we can take from the ice is we can use the ice to give us the temperatures at the time a certain layer of ice was deposited as snow. We do that by measuring the proportions of the isotopes of hydrogen or oxygen in the ice. I think that in America, science teachers maybe don't know so much about isotopes, but maybe you know how much isotopes are used for various subjects in geology, geochemistry, hydrology, meteorology. It's an increasingly used tool of great value. A water molecule is heavy or light depending on whether it is made from heavy or light isotopes of hydrogen and oxygen. From the surface of the ocean, which is the source of water for the ice, we find that the light molecules of water can jump out best into the air, get into the clouds, and then fall as snow. So we find that isotopically, the ice is lighter than the oceans. At cool times, close to equilibrium, that separation of light water molecules is most efficient. At slightly warmer times, farther from equilibrium, closer to boiling, then the separation is not so efficient, and some of the heavy molecules of water also come out. It's like distilling whiskey. If you have just a small fire, then you get only the good whiskey coming through the distillation apparatus. If you become impatient and make a large fire, then you get some bad stuff also, which gives you headaches in the morning. The same in the ocean, where at low temperatures, the separation of only the light molecules is efficient. At warmer times, there's heavier molecules of water. What we find is that in a layer of ice that came from wintertime, more light isotopes. In a layer that came from snow in summertime, more heavy isotopes. And we can make this strong association between proportions of the isotopes on one hand and temperature on the other, and we can use that to construct a historical temperature graph. So here, this is for Greenland. For the last 10,000 years, 10 is 10,000 years ago, 0 is now, and look at the temperatures, terrible temperatures. This is from the isotopes, translated into temperature. You can say, who cares about Greenland? Look at these terrible temperatures. Why do you work on this? But because the Earth's atmosphere is so quickly and efficiently mixed, the ice cores give information about wide regions. And although if we wanted to find out about places such as Massachusetts or Denmark, well, the temperatures would be different, but the shape of the curve would be about the same. Well, you see that the red pen is moving quite a lot, but if